Hey again, folks. I had a little extra time this afternoon, so we're going to make it two problems today. This is actually our final problem for the Advanced Newton's Laws playlist. In this one, we're investigating the behavior of a ball attached by two supporting strings. The plan is to snip the string on the left, which will cause our ball to swing with a pendulum-like movement to the right. We'll determine the tension in the string once it reaches position B here, and then divide that by the tension in the same string from earlier. Let's get our free body diagram started in position A. The weight of the ball will point straight down, and our first tension vector will point directly to the left. The remaining tension vector will point along the direction of the top string, up and to the right, like this. Since that second tension vector doesn't directly lie along an axis, we'll need to break it up into components using the provided angle, beta. To do that, let's draw a helpful reference line extending from the y-axis located on the ball. Since this new line is parallel to the dashed gray line here that's adjacent to our angle, we can draw beta in the following location, since it's an alternate interior angle relative to the other one. Now we're free to break up that second tension vector into components, as you see here. And that's it for position A. At position B, we can make a change to the coordinate axes to simplify our approach. Instead of an x-axis that's parallel to the ceiling and a y-axis that's parallel to the wall, let's utilize radial and transverse axes centered on the ball's location, like this. I'll move those axes to our previous position up in the top left and then draw some reference lines on our ball so we can include the new vectors. Like before, the weight of the ball will point straight downward, and the tension of the top string will point towards the ceiling again, except now it's up and to the left this time. With this new coordinate change, it's now the weight that lies off-center from the axes, and we need to break that down into components. With that finished, our free body diagrams are complete for both positions. So let's take a look at the sum of forces next at position A. Remember, we're only interested in tension 2 at this position. The behavior of tension 1 is totally irrelevant. Since that's the case, let's go ahead and ignore writing out the sum of forces in the x direction and focus our attention on the sum of forces in the y. If we move the weight over to the right-hand side and then divide both sides by the cosine of beta, we get the following. This will come in handy when calculating our answers, so let's come back to that in just a moment. At position B, we do the same process and only worry about the sum in this new y direction. Recall that the ball moved in a curved path, similar to that of a pendulum, which traced out a portion of a circle. Hence, the need to include this centripetal acceleration here. Fortunately, we're analyzing the ball at the furthest point in the swing, which means that it has an instantaneous velocity of 0 at this spot before it starts to swing back. If the velocity is 0 there, then that implies that the centripetal acceleration has to be 0 too. And this allows us to move the cosine term over to the right-hand side and get an equation for the tension of the string. Now we have both parts of the tension, and the ratio of those two quantities is no longer a mystery. We're free to plug in the quantities, and when we do the algebra properly, the weight will cancel out, and we're left with the square of the cosine of beta. Everything is now complete, and the problem is done. In the next video series, we'll be taking a look at problems involving work. Thank you all for watching, and I hope to see you there. Have a great night.